Representation of noise in circuits. Consider a general circuit with one input port and one output port. Figure, how do we quantify the effect of noise here? The natural approach would be to set the input to 0 and calculate the total noise at the output due to various sources of noise in the circuit. This is indeed how the noise is measured in the laboratory or in simulations. Here you can see the figure of noise sources in a circuit. While intuitively appealing, the output referred noise does not allow a fair comparison of the performance of different circuits because it depends on the gain. For example, as depicted in figure, if a common source stage is followed by a noiseless amplifier having, here you can see the figure, addition of gain stage to a CS stage, a voltage gain A1, then the output noise is equal to the expression in equation multiplied by A1 square. Considering only the output noise, we may conclude that as A1 increases, the output becomes the circuit becomes noisier, an incorrect result because a larger A1 also provides a proportionally higher signal level at the output. That is, the output signal to noise ratio SNR does not depend on A1. To overcome the above contrary, we usually specify the input referred noise of all circuits. Illustrated conceptually in figure. The idea is to represent the effect of all noise sources in the circuit by a single source, Vn square In bar, at the input such that the output noise. Here you can see the figure, determination of input referred noise voltage. In figure B equals that in figure A, if the voltage gain is AV, then we must have A and Vn square out bar is equals to AV square Vn square In bar. That is, the input referred noise voltage in this simple case is given by the output noise voltage given by the gain. At this point our study, we make two observations. First, the input referred noise and the input signal are both multiplied by the gain as they are processed by the circuit. Thus, the input referred noise indicates how much the input signal is corrupted by the circuit's noise. That is, how small an input the circuit can detect with acceptable SNR. For this reason, input referred noise allows a fair comparison of different circuits. Second, the input referred noise is a fictitious quantity that it cannot be measured at the input of the circuit. The two circuits of figures A and B are mathematically equivalent, but the physical circuit is still that in figure A. In the foregoing discussion, we have assumed that the input referred noise can be modeled by a single voltage source in series with the input. This is generally incomplete representation if the circuit has finite input impedance and is driven by a finite source impedance. To understand why, consider the common source stage of figure A, where the input capacitance is denoted by Cin and 1 by F noise is neglected for simplicity. From equation, the input referred noise voltage of the circuit is given by 8kT by 3 gm plus 4kT by gm square Rd. Now suppose the preceding stage is modeled by a Thevenin equivalent having an inductive output impedance. Figure B. Simplifying the circuit for noise calculation is shown in figure C. We seek to find the output noise as L1 increases. Owing to the voltage division between L1s and 1 by Cns, the effect of Vn square in bar at the gate of M1 and hence at the output vanishes as L1 approaches infinity. This result, however, is incorrect because the output noise of the circuit is equal to 8kT by 3 gm Rd square plus 4kT Rd and independent of L1 and Cin. Here you can see in this figure C a stage including input capacitance, B C a stage stimulated by a finite source impedance, C effect of single noise source. Let us summarize the problem. If the circuit has finite input impedance, modeling the input referred noise by merely a voltage source implies that the output noise vanishes as the source impedance becomes large. An incorrect conclusion. To resolve this issue, we model the input referred noise by both a series voltage source and a parallel current source figure, so that if the output impedance of the preceding stage assumes large values, thereby reducing the effect of Vn square in bar, the noise current source still flows through the finite impedance, producing noise at the input. It can be proved that Vn In square whole r and In square in bar are necessary and sufficient to represent the noise of any linear two-port circuit. Here you can see in this figure representation of noise by voltage and current sources. How do we calculate Vn square Vn in square bar and In in square bar, since the model is valid for any source impedance? We consider two extreme cases, 0 and infinite source impedances as shown in figure A. If the source impedance is 0, In in square bar flows through Vn in square bar and has no effect on the output, as the output noise measured in this case arises solely from Vn in square bar. Similarly, if the input is open, figure B, then Vn in square bar has no effect and the output noise is due to only In square in bar. Let us apply this method to the circuit of figure. Here you can see in this figure calculation of input referred noise, A voltage, B current. The reader may wonder if the use of both a voltage source and a current source to represent the input referred noise counts the noise twice. We utilize the circuit of figure as an example to demonstrate that this is not so. Considering the environment depicted in figure, we prove that the output noise is correct for any source impedance Zx, assuming Zs is noiseless for simplicity. We first calculate the total noise voltage at the gate of M1 due to Vn square bar and In square bar. How is this voltage obtained? By superposition of voltages of powers the two sources Vn in square bar and In square In square bar are in general correlated simply because they may represent the same noise mechanisms in the circuit. In fact, equations can be respectively written as Vnin is equal to Vn M1 plus 1 by GMRD, Vnrd, Vnin is equal to Cns Vn M1 plus Cns by GMRD, Vnrd, where Vn M1 denotes the gate referred noise voltage of M1 and Vnrd the noise voltage of Rd. We recognize that Vn M1 and Vnrd appear in both Vn in Vn In and In, creating a strong correlation between the two. Thus, calculation must use superposition of voltages as Vn In and Vn In were deterministic quantities. Adding the contribution to Vn In and In at node x in figure, we have Vnx equal to Vn in 1 by C in x by 1 by C in x plus Zx plus In Zx by C in x by 1 by C in x plus Zx is equals to Vn in plus In is Zx by Zx C in x plus 1. Substituting for Vn and In from equation respectively, we obtain the Vn x equal to 1 by Zx C in x plus 1 into Vn M1 plus 1 by GMRD Vnrd plus C in x Zx Vn M1 plus 1 by GMRD Vnrd is equals to Vn M1 plus 1 by GMRD Vnrd. Note that Vnx is independent of Zx, and since it flows that Vn square out bar is equals to Gm square Rd square Vnx square bar is equal to 4 kt. 4 kt is equals to 4 kt 2 by 3 Gm plus 1 by Rd into Rd square is same as equation. Thank you.